best way from the start. Because the solution for one can be harnessed by others. Because clouds that compete can still connect. Red Hat, our code is open.
Hi everyone, and welcome to the session Query Tuning Internals for the Advanced SQL Developer. This takes us behind execution plans. And as you might guess from that subtitle, if you don't know much about reading execution plans to perform query tuning, this isn't the right session for you. It'll be a little bit too advanced. You really need to understand the basics of query tuning through looking at your execution plans and discovering the red flags and things like that. I will do a brief overview of those kinds of topics, but if they are not currently in your grasp, again, I recommend that you study that before you come back to this session. My name is Kevin Kline. I'm the Principal Program Manager at SentryOne, and welcome to the session. I appreciate that you're spending the time with me, and there are so many other great sessions to choose from, so thanks very much. All right. So what are we going to talk about in a little bit more detail? Well, first of all, let me introduce myself. My name, again, Kevin Kline. I've been in this industry for many, many years. In fact, I started in the mid-'80s working at NASA. I was part of the team that built the water recycling system that's in the International Space Station, and I wrote all that code in Fortran and Oracle. So hard to believe, but they hadn't invented stored procedures yet. And so in the early 90s, I went and joined one of the world's big four accounting firms. Back then, there used to be the big six accounting firms. And so I led the data management team there through the 90s and was one of the biggest enterprises using SQL Server at that time. So I was one of the 9 people who got together and formed the International Professional Association for SQL Server, which you may have heard of. And I encourage you to join as well. Also, over the years, I've written many books. My first book I wrote in the middle 90s, and I've written 11 over the years. There will be a new edition of SQL in a Nutshell in 2021. So my bestseller, so I hope you'll check that out. Also, I've been a long time Microsoft MVP, and I also write a monthly column for a magazine called Database Trends and Applications. If you want to reach me, you can reach me at Twitter, LinkedIn, and Facebook, all 3 of those at K.E. Kline. And also you can reach me at kkline@centuryone.com. Okay, so let's move on from here. This session actually is not a full end-to-end optimizer session. If you're interested in that content, I actually have a session. It's probably my most popular session called SQL Server Internals and Architecture. And I actually have a URL for you at the end if you'd like to learn all of the nuances and ins and outs of the optimizer. And it's actually told in a way that's pretty easy to understand. So if you're not given to naturally learning those kinds of content, that's a great session for you. And this is also not a performance tuning session. Believe it or not, most of the time, you're going to get everything you need in performance tuning from reading execution plans. But what this does is this tells you how SQL Server chooses the execution plans it does. It gives you much deeper understanding of the query processor and its behaviors. So you might know, for example, that SQL Server has 3 join algorithms it can choose from: a nested loop, a merge, and a hash join. Well, this session will show you the behind-the-scenes kind of selection that SQL Server makes in choosing which of those that give it the best performance. That's what this is about, providing you an additional level of skill and understanding because you're already advanced. So this takes you much deeper. And just to make this clear as well, I'm going to show you a lot of undocumented DBCC and trace flags as well. So there'll be some interesting things there if you like to learn secrets about how SQL Server works. I also owe a debt of gratitude. Much of this I learned from people like Brian Hansen, Rob Volk, Benjamin Navarez, and of course the master of execution plans, Paul White from New Zealand. So thank you to all of you for teaching me so many of these things. All right, so let's move along. The agenda itself is going to talk about what it takes to make a good execution plan, and I'll show you some secret things you can do with that knowledge. I'll do a little bit more of a deep dive on the query processor, but again, it's not end-to-end. I'm not going to show you from start to completion. I'm going to show you the things involved with building an execution plan primarily. And then we're going to go into secrets. We're going to talk about transformation rules and heuristics. We're going to talk about the internal memo structure. And as I said, lots of undocumented stuff. So if you like to play with that, this will be a lot of fun for you. Okay? All right. So what does it take to make an execution plan? You know, when I was a big beginner working with SQL statements, it was a struggle just to get the syntax right. And that's okay, right? That's how we all start and learn. But as time went on, I began to learn about things like indexes and how important they are. So what we have today is we have three main components, but even as I was a beginner and learning, I didn't really know a lot about what SQL Server or any relational database for that matter, because I worked a lot on Oracle and some on other databases like Sybase and DB2. And so I didn't realize that there was more than the metadata component that I'm showing here on the slide. Now, when we think of metadata, most of us know that that means the data about the data. Most of us know that that also means the table schema and how that is defined, as well as any indexes that exist on that. Well, okay, so what does an index have? And what does an index need to live and offer value in a SQL Server database? Well, it needs to give you statistics. The most commonly cited statistic it's going to use will be the cardinality estimates, right? So it's going to tell you how many records on this index might satisfy a given search argument on that index. So if it has 10,000 records and 4,000 of them are likely to meet the search argument conditions, then it might give you a cardinality estimate of 4,000. Then we have other sorts of metadata that come from the indexes. We have things like density. We have things like the histogram. So the histogram is actually one level deeper than the statistics across the entire index. So that might, a table that covers last names, for example, it might say that a certain part of the index is very, very thick on last names starting with S. So in English, we have Smith, for example, is a very, very common last name. So you could have lots of Smiths, but very few Quimbys, for example, right? So it would tell you across the whole entirety of the index how many records are in each of these different histogram buckets, okay? That's important stuff. Makes a really big difference as to how well SQL Server can perform, especially if those indexes are kept up to date or they're allowed to go stale. Now, the two other main areas of information needed to make a good execution plan are the various set options. So you're probably familiar with set options like set ANSI nulls on or set arith abort on. If we have those set differently on the SQL Server than we have on our client, that can cause SQL Server to have to cache two versions of the plan. One with it set to what the client asks for, and one that's set the way that the server expects it. Another component of the set options would be your collation. And again, this can also apply to both the client and the server. So if your Windows client connects to the SQL Server, and the SQL Server has standard American style collation, but your particular workstation, let's say, has Swedish or Hebrew, then they have differing collations, which means at a binary level, values are different. And so it has to cache two different plans for that. We're not going to talk about that one at all today, that domain of those kind of set options. But we will talk about the other two, metadata, and finally the last one, which is the hardware. And so hardware is pretty simple when you think about it. SQL Server has to know a lot about the hardware for parallelism, right? So when SQL Server parallelizes a query, it splits it across all the CPUs or cores that it has available to it. That means it has to know how many CPUs or cores are available, right? And then the other main thing that SQL Server needs to learn about how much memory is available. This is extremely important for maintaining the different caches of the entire buffer pool. And then we have the data cache, the plan cache, the two biggest ones. And then we have lots more additional smaller caches like hash buckets and the sort cache and log buffers and all kinds of things like that, right? So SQL Server has to keep track of all three of those. So here's the first little secret I want to share with you in this session, which is so many times I've talked to devs and DBAs who are, trying to write some really high performance code. And one of the challenges they face is that SQL Server in production, they have a 2 terabyte database with 128 cores available and half a terabyte of RAM. But unfortunately, the laptop that we're running on has 4 cores and it has 32 gigabytes of RAM. So even if we could get that entire massive database onto our laptop, there's no way that it would perform the same or even give us similar execution plans. Well, what if I told you there is a way that we can fake all of that out and maybe have just a smaller version, just a subset of the data that's in production, let's say a 4 gigabyte version that fits easily on our laptop, and yet we could still manage to get the exact same execution plans that we have in production. So let me show you that. There is a way to do it, and it's called cloning a database. The way we clone a database, you see I've got here clone database scripting and then clone database mimicking hardware. So the first thing you have to do is generate a script to create your cloned database, okay? In order to create the script to clone your database, you start off just by generating a script, but there's a secret ingredient. And if you see script database as, don't use that one. That's a lie meant to deceive. Instead, go to tasks and then let's scroll down and then select generate script, okay? And when we generate the script, what we're going to do is take all of the objects in the database, and then the secret is under advanced, okay? Now, if you've ever generated scripts for databases in the past, you know that it creates the tables, it creates the indexes, doesn't move any data, but it doesn't do anything deeper than that. But based on what I just showed you on the previous slide, we know that there are deeper bits of information that are extremely important for making execution plans. So if you scroll down here, what I look for is the first bold-faced letters, and go up a little bit and you'll see right here, script statistics. And by default, SQL Server, when generating a script, does not script statistics for you. But we can change that. So what I'm going to do is not just choose to script statistics. That's one level deeper than the index. But I'm going to get statistics and histograms. And so I say OK to that. Now, I'm going to cancel here because I've already generated it. So there's a few things you'll need to change when you get this script. The first thing is the files and the file size. So you may not want to have 8 database files like are in production, and you may not want them to be 250 gigabytes each, right? So you'll want to change those values. They appear at the top of your script. And then the most important thing that you'll need to do is you'll see these 2 statements that say alter database, set auto create statistics on. You will need to set that off so that SQL Server will not automatically update or create its own statistics, because what we're doing is we're pulling those from production. And then finally, if we scroll down, and you'll see that there's something cool way down and buried deep in the script, something you may not have ever seen before. You will see statements here that say update statistics, and it gives the name, alternate key, sales, territory. And then it has this little string right here, this little clause with stats stream. And in addition, it's got this big long hexadecimal string. What is that? That is the literal hexadecimal representation of the indexes, the statistics, and the histogram for those various indexes in your SQL Server, okay? I mean, that's pretty darn neat. And then on top of that, you'll also see some statements here that say create statistics underscore WA such and such. Those are for when SQL Server, you've said allow auto create statistics. So when SQL Server sees a column that is treated as if it's a search argument all the time, even though it doesn't have an index, it'll start to build statistics on those as if it was an index. And so this will grab those as well. And that's the reason we don't want to allow auto create statistics and auto update statistics to run at any point in this database, because it will basically erase all of the values that we copied from production. By extension, what that means is Even if those tables are empty, SQL Server, when processing queries against those tables, will think that it has 3 billion records in it because that's what production had, okay? It'll think that this other index and table has 225 million records in it. So even though it's small, or maybe you just have a 32 megabyte version of the database locally, it will produce execution plans that are the same as what is in production based on what it knows to be true, even though you've kind of faked it out. Now remember, the second domain was the set options and collations. We're going to exclude that for now. The third domain is hardware, and that is something we can also fake out and clone for SQL Server. So in script 21, clone DB mimic hardware, what we can do is we can use some special DBCC commands that aren't widely known, but they are documented and they are official statements. So you can actually look these up and get a lot more information. And we could tell our SQL Server, what if you had 64 CPUs in terms of the hardware? What if you had a terabyte of RAM in terms of the hardware? What kind of memory grant would you give? Okay. And so when we turn these sorts of things on, let's go ahead and do that. This applies to the current session, not the entire SQL Server. So let's go ahead and execute this with the execution plan. And so what we'll see is that this plan naturally is going to be very heavily parallelized because it thinks it has a massive number of CPUs available to it. Okay, so you can see it's got a little merge join here. It does a sort because of the order by, and then it gathers all those parallel streams together. Okay. On the other hand, one of the things that we do see very frequently is that a lot of times when our organizations buy a very large server, they don't actually give you the entire server. So, it's got 64 cores in it, but we're actually going to give each of the, we're going to make virtual machines, and we're going to give each of those 4 cores. So you could go the other direction. We could say, what if we have just one CPU and 256 megabytes of RAM? Okay. So I'm going to turn that on. And again, I'm going to run my query here, and I'm going to use this option recompile so that it doesn't use the previously cached plan that has a lot of parallelism. And let's take a look at this particular execution plan. Well, as you can see, it is quite a bit different. There's no parallelism. The sort that appeared as one of the very last operations is now done very early in the query. What you get here by doing these things, by knowing that behavior of SQL Server that it uses both hardware and all of the metadata to build its execution plans, is you've learned a way to kind of fake it out, right? So that you can have a version of the production database that is much, much smaller and yet gives you the exact same execution plans that you would find in production, okay? So last thing I'm going to do is a little bit of cleanup here, and I'm going to reset this to the default of what I normally have. It does not mean that the query will execute in the same amount of time. So don't judge it in terms of performance. Judge it in terms of the execution plan, which will now give you the opportunity to look for red flags that you can tune and get out of there. So let's move on. SQL Server is well known that most of the time when a query completes, if you look at the deeper level of information available to you, it will say good enough plan found. And that's why it stops processing. And so SQL Server tries to give us a good enough plan. It doesn't try to give us what you might actually define as a good plan. And it definitely doesn't try to give you the best plan. And the reason for that between good enough and good is when you balance those scales out, a really good plan might take the optimizer a long, long time. So let me illustrate that for you here. Let's do the math. We have a SQL Server database with lots of tables, and we're going to write a query that is basically a 4-table join. Okay. Each of these 4 tables has one clustered index and 3 non-clustered indexes. And so we're going to do a join across all 4 of these tables. Select some columns from table A, join to column B on the key, join to column C on the key, join to column D on the key. That's not a very sophisticated SQL query when you think about it. But what does this mean for the optimizer? Well, for one thing, each table has 72 different physical access methods by which we can get to the data we might need. We could have a clustered ordered seek and a partial scan. We could have a non-clustered order seek and a partial scan. We could have a covering index. We could have a non-covering index. We could have a key or a row ID lookup with all kinds of things. So you multiply that by 4 because we have 4 tables. Then on top of that, and this is something I will talk about in a little bit more detail, we have logical join order processing, okay? And so what SQL Server is trying to do is it's trying to carry as few records forward through all of the steps of the execution plan when we look at the execution plan. So if we were to join A to B to C to D, and each of those tables had 250,000 records, and we did it just in that order, that might mean we have to carry all 1 million records all the way through. But if on the other hand, we join table D to table C first, because of the join criteria, it would actually eliminate 500,000 records. Well, that's good. We don't need as much memory at every step of the way to make that happen. So SQL Server will reorder all of the different joins to see if any of those will happen faster. And then finally, we have a few other things SQL Server might do. For example, it might join based on a merge, a hash, or a nested loop. So it might join any of those methods. It might require sorts that go to tempdb or spills that go to tempdb. To add it all up, a 4-table join with 1 clustered index and 3 non-clustered indexes is about 26,000 different options for the optimizer to get through that process. So to be honest, I'm kind of pleased that we do get answers as quickly as we do a lot of the time. There's kind of a joke about this. The optimizer goes fast, and this is the reason it chooses a good enough plan. You know, when you look at strategy A versus strategy B, you can see strategy A is a hair faster than strategy B, but the time it takes to compare those different strategies is 100 times longer than just to go with one of them. Even if it was B, it'd still be a heck of a lot better than to try and analyze all those options. So that's why SQL Server makes the choice. When it's found a good enough plan, it just goes with it rather than analyzing a bunch of other options in the hope that maybe we find something better, okay? Now, as I mentioned, it does these different kinds of transformations. That's the key word that they use, such as when we rearranged all the join orders. And so I will tell you a little bit more about these different kinds of transformations, and I'll show you some examples. Simplification, exploration, implementation, and then another called physical property enforcement. So let's go a little bit deeper on the query processing set of activities. Now we're going to mark off these last 2 entirely. We're not going to talk about converting to an executable plan or hand off to the storage engine, but we are going to talk about each of these in a bit more detail as we go along. And I'm going to do some demos of these different concepts as well as some of the transformations that may happen along the way. The first thing I want you to know about the 4 across the top. The average person, though, who's written a lot of SQL queries probably only knows about parsing and the trivial plan. And one thing that's interesting, though, about all 4 of these steps as they happen in order is that you actually don't really even need any of the metadata that we just talked about. All you need is the definition of the table or tables involved, including any indexes that they have, as well as the definition of the query itself. Then based on that, it's able to do its parsing, binding, simplification, and trivial plan. So it doesn't need things like any of the data. It doesn't need things like the statistics or the histogram. It doesn't make cost estimations or make cost-based decisions, okay? So let's talk about these in just a bit more detail, starting with parsing and binding. Parsing is sometimes also called the algebraizer or the normalizer, based on the original set of foundational theories of relational algebra and set theory. Its most well-known job is to validate syntax. You know, so if you type in SEELCT instead of SELECT, you know, you misspelled the word select. then it'll kick back and say, hey, I don't understand this. What are you saying to me? But it does a few more things. It also identifies constants and variables. It expands views out. And then it'll build something called the logical parse tree. I'm going to skip that entirely. I have other sessions that go into it in detail if you want to know about that. Now, one of the things about parsing and also with binding is SQL Server wants it to fail quickly and early, because if there's any syntax errors, if there's any permission errors, which happens at the binding phase, let's do that now without wasting all the energy of going through the rest of that roadmap of particular processes and operations. Let's not waste CPU. Let's let it fail early so that the user can rewrite their query so it doesn't have that problem again. Okay. Now in the binding phase, what we do is we now know based on the parser that that table exists, but do you have permissions to that? If you're doing set operations like union, intersect, and minus, all of those require ordinal position matching between the two tables. And what if there's a data type problem between them? What if there's aggregation? What if there's a plan that's already been generated that does all of this and it's already in the plan cache? That all happens at the binding phase, okay? So let's take a quick look at this and see a little bit about this in demo. So one of the first things that I do want to mention to everyone, if you're brand new to query tuning and you've stuck with me so far, the main thing that you will use most of the time is the execution plan to tell if a query is problematic or not. There are red flags in those operators when you look at an execution plan. So you want to look for sort operators, you want to look for spools, like an eager spool or a lazy spool. You want to look for key look operations that are costly. So maybe key operators or row ID, RID lookup operators that are 40, 50% or more of the cost of the query, okay? And then in order to get good performance out of your queries, typically it involves you creating search arguments, which are also called SARGs, creating search arguments on index columns so that you can filter out any unwanted data quickly and get your result set quickly. So search arguments are almost always on the where clause, on your join clause, and sometimes on clauses like having. So one of the things that's, let's take a look at a couple execution plans just in case you've never seen one. For example, I'm going to look at the sales order ID in the sales order header table where the salesperson ID is equal to 283, okay? Comes back with a result set right away. And when we look at the execution plan, we see that couldn't be simpler. It's basically an index seek. So what it is able to do is it's able to go to the index that exists on that column and go straight to the singleton row or perhaps many rows that have that salesperson ID equals to 283. And then it can, because every non-clustered index has a pointer to the row on the clustered index, it can jump over and retrieve all the data you need very quickly. And as we see here on that little pop-up box, the number of rows read is 189. Now here's something I want to teach you that again is a secret. I mentioned how relational databases and the way they execute queries is based on relational algebra and set theory. And there's also some relational calculus in there as well. Well, one of the things that these excel at, these relational databases, is finding sets of data. However, what if you want to ask for not a set? Okay, so I want to find all the values that are not equal to salesperson 283. Okay, it's just the inverse of the query that we just ran. So when we execute this, what do you think the chances are that we're going to have a nice simple query plan? Let's look. Wow, that's, the other query plan just had 2 steps, index seek and giving you the results. Here we see we have all kinds of steps, constant scan, then compute scalar, then concatenation, then compute scalar, then a sort. And sort's one of those red flag operators that can actually be very expensive. Okay, well, what's going on here? Well, what is happening in SQL Server, and again, this will happen in all the relational databases, is that they're great at finding sets, but in order to find not a set, they have to pull together all the sets that exist, examine them, and discard them as they go through. And what they have left over is the result set. So it's very uncomfortable processing for that relational database. However, if you have a query that needs optimal performance, now I would still use that syntax 85 to 95% of the time, depending on what kind of queries they were doing. But if you had some kind of query that was taking hours or more to process, here's an interesting thought. I can get the functional equivalent of not equal to 283 by saying where the salesperson ID is greater than 283 or it's less than 283. So basically not equal to 283, but because those result sets are defined as two distinct sets, here's my result set now. Look at that. The execution plan is as simple as it was at the very start. That's because they are great at finding sets of data, okay? And a set can be not just a singleton evaluation, but it could be greater than or equal to or less than or equal to. So again, as long as it's a set, it will be quite quick and the execution plan will be very simple. However, what about subqueries or things like that? So here I could say where it's in a subquery that returns a result set. And basically I do have two distinct tables. So I'm going to have hopefully two index seeks. Sure enough, there I do. And I have a simple nested loop join to bring them together. But what if I said where it's not in, or if I were to say it does not exist in this subquery? What are we going to get there? Take a look. A very much more extravagant execution plan than the inverse where we're just looking for a set. So in a case like this, I could probably rewrite this as a left outer join, and I would be back to the same structure I had before where I had two seeks, nested loop join, and then my result set. So something to keep in mind. Another key thing to keep in mind is that when you put a function call, whether that's a user-defined function or just a system function on an indexed column, you also do the same sort of thing there in that you invalidate SQL Server's ability to fully exploit the potential of that column. So when we look at this execution plan, what we'll see is, yes, it was able to use the index, but it couldn't use a seek. It had to use an index scan. And so that is more time consuming and intensive than just doing that index seek like we hoped to be able to use. So that's a little bit about the basics of execution plans. Again, this is not an execution plan session though. So let's talk about parsing. You probably know that the parser is something that you can engage. If I say set parse only on, and then I ask it to check the syntax here, it doesn't actually complete the full query. It just checks the syntax. Let me turn that off. Now, one of the things that does get some folks, set parse only on, and I execute this query, I execute this query, I don't have this named column, and I don't have this named table. When I execute this, though, it says, oh, it checks, it parses just fine, even though they do not exist, okay? What is happening here is SQL Server has a feature called deferred name resolution. And what that means is I'm not going to check for the existence of those objects at compile time. I'm going to check for the existence of those objects at execution time. And the reason for that is because you may have written a stored procedure or a trigger or some other kind of conditional code that has multiple steps and so forth, where you create the table up at the top and later on refer to the table in code that's further down. So as a matter of course, Microsoft doesn't make you have to make sure the table name exists until execution, deferred name resolution. Now, I told you about binding and some of the things it does. So let's say, for example, we're going to union two columns together. Now, the rules for union says that each column in each of the different select statements of the union must have the same data type or compatible data type in each ordinal position. So here we have two ID columns, and do you think it's going to work? It does, because the IDs are both ints or perhaps big ints. However, what if we add first name to the first select statement? That's a varchar. And we add order date to the second one. And dates are not natively compatible with the different character types. So let's see what happens here. And notice that we get a conversion or a failure very early in the process, just during the binding process, so that it never tries to even execute these queries, okay? Similarly, the binder will catch when we have mistakes in the way we aggregate values. So if we're using something like a count or average or max or min or any standard deviation, any of those kind of aggregate functions, we have to reference every column that isn't in the aggregation as part of our group by. So if I had group by last name and first name, that's proper syntax. But here, I'm going to get a failure because I haven't included the first name column in that group by statement. Simplification. It does some amazing things. I remember when the simplification engine got powerful in SQL servers back in the 6.5 and 7.0 days of SQL Server in the 90s. Back in those days, you could actually write two versions of a query that returned the same result set, one using joins and then the other using subqueries, and you get very different execution plans. Now, though, what SQL Server does behind the scenes at the simplification phase is it says, oh, you've written a subquery, let me turn that into a join for you. And so it completely changes that. So as I say there, it does things like convert subqueries to joins, converts inner joins to outer joins under specific circumstances. Let's say you have multiple joins that are the same. Well, we don't need those. So let's remove that redundancy to make it faster. It'll do things like contradiction detection and predicate pushdown. So let me show you a couple examples of how SQL Server does that. Now, here's the first DBCC statement that you need to learn if you don't already know this one. Many of the undocumented DBCC statements that I'll show you as we go along are invisible unless you tell it to surface these result sets to the console. So 8606 actually enables us to see some of the internal parse trees that SQL Server constructs, okay? So here's an example in which what we're going to do is we're going to query this particular join, but it's written as a subquery, and we'll see where SQL turns this from a subquery into a join, okay? So where's the results? It's over here under the Messages tab. Okay, so this is the first tree, and notice here we've got a logical operation projection. That means it's a select statement, and next thing it does is logical operation select, get from a table, blah, 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 blah. And then as we go down, we'll see a little bit further here, all of the different work being done in the subquery as well. When we go to the simplification phase here, notice what it does. Instead of having a logical select, it has now brought up to the very first step. I'm going to turn this into a left semi-join. And then we see the select statement. And then we see the comparison operator right here, comparison equality. So it's actually a simpler parse tree at this stage, simply by pulling all of that subquery into a join. Okay, now here's another example. This is a really kind of complex query. Let's go ahead and just select the query. We'll turn on our execution plans, and let's just execute the common table expression, the CTE here, to see what this query looks like. So there's a big result set. It's still taking a few moments to process. We haven't even gotten our execution plan yet because it's still processing. All right, there it is. So we look at this plan and we can see, wow, you know, it's quite a sophisticated execution plan. We've got parallelism throughout. We've got some clustered index scans, so it's reading the whole table. We've got hash matches, which are expensive ways to match a join data, because every hash match always has to produce the hash output and put it into tempdb. So that means it's spooling or spilling out to tempdb each time. So let's go ahead and execute this particular piece of code, and we'll see what happens. So let's look at this execution plan now. What? It's got one simple step to do an index scan and it returns the data to us? Well, what it has done, if we were actually to look inside of here, and if I had put the parse tree trace flag on it, what we would see is that it compressed this entire CTE down to this simple query right here. Because everything that we selected in the outer query of the CTE all came from the same base table, not all three tables. So it says, oh, I don't need to worry about those joins. Let me get rid of those joins and just pull that one set of data out for you, okay? Now, another thing I mentioned is predicate pushdown. So what that does is that's another way for SQL Server to actually push different functions of filtering out further down, lower into the execution plan so that SQL Server doesn't have to pull large sets of data up through its operator pipeline to the final conclusion. Let's eliminate as many rows as early as we can. So again, let's take a look here and see what we have. Again, this will be under the Messages tab. Take a look under the Simplified Tree once again. So here's an input tree. It's not what we're looking for. Here's the simplified tree. Notice that we've got the join up at the top, and then down below we have all of our our different comparisons. Whereas in the input, first thing we have is the select operation and then the join. But with predicate pushdown, we're able to bring the join up and the select down to get better, faster results. Foreign key removal. Again, the idea here is we have a foreign key on one of these tables. It's a fully trusted foreign key. And so we know that this query can't actually have values that are not present in the table where the foreign key points to. You know, it's a means of making sure our data is very high quality. And so when we execute this, what we will see is that SQL Server, during the simplification phase, says, you know what? I don't actually have to do the join because this foreign key exists, and so I can collapse that down during the join collapse phase. So if we look here, we see, again, the logical join operation. That happens early, but now let's go down to the join collapse phase. And what we see here is that it has a different set of output because it said, you know, I don't even need to do that join to the other table. This key has always been trusted. I know for a fact that when the data is inserted into this table, that the foreign key ensures that the data exists in the second table. And then finally, contradiction detection, which is really cool. What contradiction detection does is it says, all right, I know for a fact that a particular column, for example, cannot have two values at once. So if we were to say, return all this data using a join between these two tables, and the unit price is greater than 50, and the unit price is less than 25, now I can't do that. That's a contradiction. You can't have both of those be true at the same time. Now, one of the things I am a little puzzled about is that instead of giving us an error, it basically just always shows us a null result set. But if we were to look at the execution plan, we would see that it doesn't have to do that, basically any of the processing, because it knows there's a contradiction present in this case. Okay, so that's simplification. Very powerful phase, the behavior of SQL Server. Now, with trivial plans are the last phase before we go to full optimization of a SQL statement. And basically, with a trivial plan, SQL Server looks at the table and the schema definition, and it says, how many ways do I have to solve this query? If there's only one way to solve it, or one obvious best way to solve it, it doesn't even go to the trouble of going further into the optimization process. For that matter, once the query is executed, it doesn't even bother storing the trivial plan in the plan cache because it's so easy to create a new version of that, right? Anytime somebody asks for it, we can create a new one without any problem at all. So again, I do have some examples of that in the code in case you're interested. So this particular table, if I say, let's just get the estimated execution plan here. And I'll press down here, I will press the F4 key to pull up additional information over here on the right-hand side. And notice here when I click on the final step, it says optimization level is trivial. So there's no choices on how to solve this. Basically, this particular table has a clustered index. And so if you say, give me all of the records from this table, the only way it can resolve that is to do a clustered index scan. Okay, simple as that. If it didn't have a clustered index, it would have to do a full table scan. Now, in the example here, which I'm not going to take the time to do because we're running late, but if I were to add an index, and now I do a query that requires that index, now SQL Server has options. It can use the non-clustered index to perform the query and give it the records it wants, or it can use the clustered index. And the minute you give SQL Server even one additional choice to best solve the query, that means it's going to skip the trivial plan step and go to the 3 phases of query optimization, which we are going to talk about in just a moment. So when SQL Server goes to optimization, it does a couple things before it actually starts to optimize. One is it loads all of that metadata that we talked about. Remember, these first 4 don't need things like the cardinality estimates, the histograms, the statistics, the density, and so forth. It then also goes to the next step of doing all of that associative properties of joins and reorders the joins to see which of those will eliminate the most records earliest in the process. So those 2 things happen. And then it goes to the 3 phases of optimization, phase 0, 1, and 2, or sometimes called search 1, search 2, and so forth. So let's talk about that. When we're at phase 0 to produce a transactional plan, the idea here is a singleton insert, update, or delete, or maybe a small multi-row select statement. SQL Server is doing plan matching. For example, one of the rules at phase 0 is no more than, I believe it's either no more than 2 tables or no more than 2 joins. So if there's just 1 join, it might use phase 0, for example. And what it's doing is it's doing simple row and pattern matching. So I know this is a query that has a nested loop and there's no parallelism. So all I have to do is phase 0, transactional plan, quick and done. Immediately after that, we're still doing that kind of pattern matching to give us what's called a quick plan, but these are still a very limited number of plans. It's got more transformational rules, things like some additional join reordering, limited parallelism, medium kind of cost threshold. Again, what it's doing is it's looking for plan shapes. Oh, this has 3. It has the base table and joins to 2 other tables, 3 tables in all. All right. I'll compare this with a serial plan and a parallelized plan to see which does better. So that's a quick plan. But most of the time, SQL Server will go to a full plan. And instead of doing that plan matching, what it does is plan pruning. So the optimizer has thousands and thousands of different rules it can apply, and that it has to apply in certain circumstances. For example, anytime you have a data type that is a max data type, so var binary max, varchar max, char max, it has to use different rules than if it is not, if it's varchar 1000, something like that. So if you have no queries or tables or anything like that that use max, then it can prune off that entire branch of heuristics and costing algorithms for calculating the cost of columns that have data types that are max. And so that's what it's looking to do. It's no longer trying to match it. And now it knows I got to do all kinds of things, and I got to do it as quickly as I can because you're an angry human being who knows how to turn off the computer where I live. So it's trying to satisfy you as quickly as it can. Okay. And so that's what happens in those phases of optimization. And so these are some of the things that it applies as it goes throughout. I mentioned that there were different kinds of transformations. So the exploration transformations happen at a logical level. And remember algebra? relational algebra that I mentioned at the beginning. If you remember in algebra, we had the commutative, the associative, and the transitive rules. And so that's the sort of thing that it applies. Quick quiz here. Which of these are we not seeing in the list? We're not seeing the transitive rule. And in the old days, again, up through about SQL Server 2000, if you had, let's say, a 3-table join, all of them on a business entity ID. So join table A business entity ID to table 2 business entity ID, and then table 2 business entity ID to table 3 business entity ID. You haven't taken the transitive property all the way to its conclusion, which is if A equals B and B equals C, therefore we know A equals C. So all the way up through about SQL 2000, if you had really big tables and then you included an extra join that was for A back to C, you'd get better performance. I have experimented with this in later versions, and you still get better performance if you do that. It's just negligible. So unless you have a gigantic database, I wouldn't encourage you to do that kind of additional work right now. So that's one kind of transformation. And another one is implementation transformations. So this starts from the logical standpoint, but then it moves into the physical standpoint. For example, SQL Server might choose to do a merge join because it looks at the actual data in the table and it sees that they're exactly the same. And so a merge join operates kind of like a zipper, where it compares each record based on the primary key going down through each of the tables. So it might say, oh, you know what? I think a merge is better than a nested loop because of the physical aspects of what we have in the database. Okay. And then we have those physical property enforcement transformations. So like when you put a ascending order by such and such value ascending, but the column is stored in descending order for some reason, that means it's going to have to physically change things. It's going to have to enforce that physical property that you requested of it. Or you look for something that has a check constraint, or you have a merge join, or what would normally be a merge join, but you have sort orders that are inverted on 2 tables. So now SQL Server has to figure out how to handle that physical property in the best way possible. Now, that's what we see when we look at an execution plan. We see what SQL Server chose, but we don't see how SQL Server chose it. We don't see the many different options that SQL Server may have looked at. And so that's where the next part of this demonstration comes in, is the internal memo structure. This is how SQL Server chooses between its many different options. So here we have a situation, this is what it looks like. And we do have some unusual syntax that SQL Server uses. So logical operation group by aggregate. Ancillary operation projection list. Projection means select, right? Further down, you can see scalar operation comparison, scalar operation identifier. I have a little script for you in the script library where you can play with these commands and look at the results in the internal memo structure to learn as you go along what all of these externally facing things, like when we see a clustered index scan, what its nomenclature is behind the scenes as something like logical operation join, So what does all this mean? Well, this is the entry number, and this is the internal initial memo structure. So everything in the initial memo structure is the logical operations. And it's going to all be 0 because this is all logical at this phase. Then it tells us what that logical operation is, and it points to all of the different child groups. So all of the things that led to it making its decision that this logical operation of join would be best, okay? And then also you'll see everywhere it says card, that means cardinality estimation, okay? I like to look at the internal memo structure to see where it started, but the final memo structure is also probably more important. And one thing you'll notice here is that it's bigger, okay? And the reason for that is twofold. First of all, you'll see all the physical operations. So physical operations stream group by aggregate. And we see what the cost of this step is. Notice down here, we've got 2 options, group number 9 and group number 7. One is a cross apply and one is a merge join, and it's comparing the 2 costs of those. So the cross apply is 0.350 and the merge join is 0.0300. Okay, just going 4 digits out. And so clearly we can see the merge join is going to be a cheaper operation than the cross apply. The other thing that can make the final memo structure bigger is that it's possible for SQL Server to have two basic plans in here, one serialized and the other parallelized. So that can also make it quite a bit bigger. But again, the idea here is we wonder, okay, well, SQL Server had a lot of different ways it could solve this query. So why did it choose, why didn't it ever do a cross apply? And so you go to all the trouble to rewrite the query as a cross apply to compare the two, when in fact, if you knew how to apply the final memo structure code, you could find out what it had tried. So that's the next section that I have here in the demo for you. Again, we have to use trace flag 3604. And in this case, my favorite is to use trace flag 8615. And sometimes I use 8757. That turns off trivial plans in case that might be a possibility. And so again, I've got the execution plan here, but now, and again, it's just a single clustered index scan, but I can see what else it might have tried to do. So it just did a logical get operation, and then it did a physical range scan. There are a number of really cool trace flags that I have for you to check out in this in the demo code, so I encourage you to download it. This particular one, again, is going to show us the final memo structure. And as we go down through the process, we can see here's a range scan, here's a physical hash join algorithm, another range scan, filter, and so forth. So really, this particular query, because it's so simple, didn't have a lot of things to compare one to another. It just went straight through and found a good enough plan. I mentioned some other bits of code that you can look at. For example, if you are interested in those heuristics, I have a series of queries that show you the heuristics each time with a little bit of added code, SQL code to it, so you can see as it builds more and more functionality into the query, what the correlating inner nomenclature is. So this query is called Explore the Optimizer Rule Nomenclature. There are some commands also that will show you what the nomenclature is. So if you look at undocumented DBCC and optimizer rule nomenclature, you'll see I can actually just say, hey, show me all the rules that are turned on for this particular SQL server, and it'll give you that whole result set. Join to nested loop, left outer join to nested loop, full outer join to merge. SM in this case means merge. So pretty neat stuff. Another thing that is interesting is some cool things about DBCC. So if you use this DBCC trace on 258, what this does is it will even give you the help for undocumented DBC statements. Pretty cool. So here I'll turn on the output, the console output. And if I say DBCC help with a question mark, it will show me all the supported statements for this particular version of SQL Server. I'm currently running SQL Server 2017. Now, if I say SQL Server help and I put that particular command inside of that statement, you'll see the full syntax there, okay? But if I run this trace flag 2588, and now I execute this command, help, to see all the commands that I can get help on, I have a whole bunch of DBCC commands that I had never heard of before. What's DBCC buffer? Here I have autopilot. Let's put buffer in just to see what that looks like. And so when you execute this particular query, now you can get information on what this is all about. And if you then Googled on DBCC buffer, chances are someone has written a blog post on that now, okay? I have another query around advanced instrumentation and DMVs and things that you may not have heard of. Don't have time for that. And then the last thing I do want to show you, we have the final memo structure, but remember how we talked about how a query plan, SQL Server always tries to give you a good enough plan. It turns out, over the years, there were plenty of times where I wanted SQL Server to take more time and build the very best execution plan it could, because it was used so much and so heavily that even if I shaved just a couple cycles off of it, it would give me better performance. Well, it turns out there is a trace flag that does that. It's trace flag 8780. And it doesn't literally give the optimizer more time. It gives it more probes down differing branches of the heuristics tree. Even though it may give you a different execution plan, it doesn't necessarily give you one, because it could be the best one that it has found is the one you have. And it also doesn't mean that that alternative plan will be better. I also don't want you to ever tell Microsoft that I told you about this, okay? So here we have some different queries that I've added and put together. One thing I've learned is that it does not give you any improvement in performance with less than 4 tables joined in a single query. It has to be a relatively sophisticated SQL statement if you want to get anywhere with that. I will tell you this, I don't have time to demo each of these, but here's the original query. And then when we put it with 8780 added onto it, it does indeed produce a different execution plan that's about 18% faster, okay? So sometimes it's great, sometimes it's a waste of time. But at the end of the day, you may have one query in 1,000 that is worth that extra time. And so that's what you want to use to see if you can find that better execution plan. And then you could use something like a plan substitution, a forced plan, to make it choose the alternative, okay? I also have one more script that shows you all kinds of other trace flags that can be really useful and really interesting. For example, there's one trace flag that I really like. It's 8621, and then it shows you the different rules that SQL Server is using behind the scenes to actually produce that result set for you. And so it'll tell you if it's using, logical operation group by aggregate, something like that. Okay. So hopefully I've given you more resources than you needed when we started. And let's wrap up. First thing is, these are all of the trace flags that I mentioned in the different scripts that I have demoed. Okay. So don't fear that you won't have gotten all of these written down in time if you were taking notes. The second thing is I have a much deeper dive on the behavior of SQL Server in processing queries. And so if you want to learn about how SQL Server does all of that, and it's done in a very narrative style rather than just hitting you with a ton of facts, check it out. It's called SQL Server Internals and Architecture, and it's on my website, century1.com. And then let's summarize. So what are the steps in the optimization search phases? We've got 0, 1, and 2, but those are actually, we have the trivial plan, we have the transactional plan, the quick plan, and the full plan. And then what were those transformations that SQL Server does? We have the simplification, we have the exploration, implementation, and the physical enforcement transformations that it does. What does the memo structure tell us? That's trace flag 8615 for the final memo structure, and it tells us the different alternatives that SQL Server considered before it produced the execution plan. The execution plan is the output from that set of work that it did to build the internal memo structure. And then finally, some of those cool trace flags. You always need to know 3604 so that you can get output from these things that normally hide the output. There's 8615, 8605, so many of the different trace flags that tell you various bits and pieces of what happens behind the scenes. And again, demos for all of that in the script library. And then finally, trace flag 8780 for that utterly, crucially important query that takes a lot of time and energy. This is an opportunity for SQL Server to give you an alternative and probably, but not guaranteed, to be a better performing plan. That was a lot, wasn't it? So let me say thank you. I hope you'll add me to your Twitter list. If you're on Facebook or LinkedIn, you'll add me there. Thank you. And I have additional slides and scripts at century1.k/Kline. And I have videos, slides, and scripts at century1.com/webinars. We also make a free, fantastic query tuning tool that doesn't even ask or require an email address called Plan Explorer. So I really hope you'll download that and start to use it as well. And with that, I'd like to say thank you very much. I appreciate your time and look forward to answering your questions.
Because we've been this way from the start. Because the solution for one can be harnessed by others. Because clouds that compete can still connect. Red Hat, our code is open.